you so much for having me. My name is Ramsey Nasser, and I'm excited to talk to you about a compiler that I worked on for about 5 years, all things said. The title of the talk is What's So Hard About Writing a Compiler Anyway? And that's also going to be the two sort of parts of the talk. I want to talk about how writing a compiler is actually not that hard, and then I want to talk about So this is where I live on the internet. It's my website, my GitHub, my Mastodon, and my Twitter. So if you're interested in this kind of stuff, that's where I post things generally. So I'm based in Brooklyn for the most part. I'm currently in Philadelphia right now because of scheduling, and I'm on site installing an interactive piece in the museum. But in any other circumstances, I'd be broadcasting from Brooklyn. So the compiler I want to talk to you about is called Magic. It's the Morgan and Grand iron Clojure compiler. Magic is a compiler for Clojure written in Clojure, targeting the common language runtime. That's the virtual machine that C# runs on. And I started Magic in about 2000, I think the first commits are 2015, and I got it about 60% of the way done by 2018. And we actually got, sort of through a long story, got some funding to get the last sort of bit of it done, and that all landed in 2020. So as of the middle of 2020, Magic is feature complete. It passes the Clojure test suite. It is self-hosting, so it builds itself, and the REPL that I use, my Clojure REPL is Magic, basically. It's having, it all runs through Magic. So I didn't really think it would happen, but it actually got over the finish line, and that last sprint of the last 20% is kind of the sort of the interesting part of the story. A lot of that is where the O part comes from. So it's called the Morgan and Grand iron Clojure compiler. So Morgan and Grand is the names of the cross streets of the building where the bulk of the initial design and work was done. This is the kitchen table coder studio in Bushwick in Brooklyn, where I was at for a number of years. It is at the corner of Morgan Avenue and Grand Street. I shared space here with David Nolan and Kovas Bakuda, both of which they didn't directly work on the compiler or anything, but watching David work on ClojureScript and watching Kovas work on a framework called Gamma, which was a ClojureScript compiler for GLSL, the shader language. Watching them work was extremely formative and really guided the design of the philosophy of Magic. And that's also where I met Tim Gardner, who has been a lifelong friend and business partner ever since. And Tim's is the person with whom I built a framework called Arcadia, which is a sort of a way to run Clojure inside of Unity, which is Unity is its industry standard video game engine. And that's all on the CLR. And Magic was built basically to support the Arcadia project to make it a little bit more performant and to reach targets that we couldn't reach. But I'll get into those details down the line. The one last person that I'll mention is, so Clojure on the CLR is not something that we invented by any stretch. It's an official version of Clojure, although many people don't know that. It's primarily maintained by a man named David Miller, who has done this sort of incredible, heroic work of maintaining this feature complete fork of Clojure off to the side of the JVM and the JavaScript implementations. So David Miller's implementation is what we built Arcadia on initially, and then to address performance issues and export issues, Magic is what we did. So so that's Morgan and Grand. Iron is this I don't really understand it, but it's what people call languages that run on the .NET framework. So there's an iron Python and an iron Ruby and an iron Scheme. So Magic is the iron Clojure. This is sort of what the rough pipeline looks like, right? Clojure source code comes in, Magic takes it, and it produces bytecode in the common intermediate language, the CIL. That is the that is the bytecode. It's the same bytecode that the C# compiler emits. I've given talks about magic where people who just assume that Clojure runs on the JVM were like very curious, like how we were piping data to the JVM and back to the CLR so quickly. It's like, oh, how are you doing that? It's like, no, it's all, we never leave. There's no Java dependencies. We never leave the CLR. It's all just the C# tooling. So, on and off for 5 years, about 2 years of work, I would say, if I sort of added them all up, is what went into this. So like I said, there's two broad parts of this talk. The first is a sort of exploration of the perception of compilers as like these hard things that are sort of impossible to do, and the fact that, if it's functional and you're compiling for a Lisp, it's actually a compiler is not that hard to do. So the takeaway from this section is that, if anyone is like listening or watching this and has been thinking about doing a compiler, but didn't want to do it because it's maybe too hard, it's like, you should go and do it. You're completely within the realm of like what you can do as a software developer, right? So I had always been interested in programming languages from, I think the moment I started writing code. And I had done interpreters and like little compilers before, but Magic is definitely my first like at scale big compiler for like a mainstream language. And I tend to learn by doing. And this is a question that I legitimately came into the project with. It's like, what is actually hard about doing this stuff, right? And the process of building Magic sort of provided me with some of those answers. This is the standard compiler textbook that they'll give you in school if you study programming language theory, and it's like a dragon sticking its head out of a computer. And I love this image so much because it just tells the story of what computer science as a practice thinks of compiler development. It might kill you, which is just it's just such a wrong way to, I think about compilers. And it feels more like this to me. It's like, it is a dragon, but it's nice, it's friendly, it's got its soft edges, and and I would love it if they replaced the book cover with this image. So like I said, I'm in Philadelphia and I do interactive installation work, and I'm installing a 34-foot 360 video interactive wall in a museum. And yeah, building a compiler is hard, but like that's harder. Like in a compiler, if the user gives you invalid input, you shout at them. You don't get to do that in an interactive installation. If the user gives you invalid input, you need to account for that and not break the magic. And so the edge cases are much more sprawling, I think, in interactive real-time work. And this is true for people who do front-end development and UI development. Like anything that a human is touching is I find categorically harder than like a compiler, which we'll see is just a nice functional pipeline for the most part. So this is the 10,000-foot view of the architecture of Magic. And to sort of like think about like the straightforward aspects of compiler design, I find it easy to like look at something concrete. So I'm going to talk a little bit about like how Magic actually approaches the problems that it has to solve. So there are, broadly speaking, 4 phases. The first thing that happens is a reader takes your source code and produces S expressions. So this is a classic Lisp first move. There is no parser, right? Because we don't have syntax and we don't want syntax. The reader sort of produces lists, and in Clojure's case, symbols, keywords, vectors, hash maps. You get this nice data. An analyzer takes that. I think some people say that in Lisp you're programming in the abstract syntax tree, but that's actually not true. Generally, that's not true, especially for high performance Lisp compilers. So the job of the analyzer is to take the S expressions and produce what's called an abstract syntax tree, which is a different data structure that represents the user's code. And I like to think of S expressions as like what the user said, and the abstract syntax tree as what the user meant. And we'll look at the AST in detail in a couple of slides. The AST then is fed to what in Magic I call a compiler. A better name for it would have been the code generation phase. That's what other compilers call it. But this was when I started working on the project, this was the core of magic, was just the thing that produced the bytecode. So the compiler takes the syntax tree. So now we know what the user meant. And now we have to produce bytecode. And we actually do that in 2 steps. Magic produces what I call symbolic bytecode, which is a functional Clojure data representation of the bytecode that will eventually run on the CLR. And that's fed to an emitter, which is actually an external library that I wrote to produce the actual bytecode. And the reason it's broken up into those 2 steps at the end is because writing bytecode into memory is a very mutable, very gross, very hosty operation. You're talking to like C# APIs, they're all object oriented, they're all mutable, and they're just like very like difficult to reason with. So one of my absolute favorite things that sort of Clojure provides, not just as a language, but as a philosophy, is that the way you deal with those sort of like unfortunate messy bits is you sort of wrap them in this like functional representation. And that's why the emission step is broken up into 2. So for the purposes of time, we're not going to spend too much time on emission. Just going to focus on the sort of the middle parts of the compiler. So to like make that a little bit more concrete, I sort of want to walk through like how the sausage gets made, and I want to look at like how an expression like plus 1, 2, 3 becomes 6 in magic. So the first thing we do is we read the string. Magic does not provide its own reader, but sort of on purpose, because we want to be compatible with stock Clojure. So we use the standard Clojure read string, and which will produce, it will invoke Clojure's reader, and it'll produce the S expressions for you. So here it gives you a list with 4 elements, the plus symbol, and then the longs 1, 2, and 3. Nothing, so very standard, nothing fancy here. So if you look, I'm going to use my cursor to sort of point at things. So if we take the results of read string and we pass it to the analyzer, we'll see the syntax tree. And the analyzer is based on a library called Tools Analyzer, which was written by Nicola Mameda. So this is a cross-Clojure analysis framework that can take S expressions and produce these syntax tree nodes. And because it's written in and for Clojure, the syntax tree is just sort of loosely structured hash maps, which is a dream to work with. So every hash map has an op key that tells you like what sort of the kind of the hash map that you're looking at, the kind of the ASC node that you're looking at, and it might have a children key. So some expressions basically have sub-expressions, and the children key will tell you what other keys to recurse into and to treat as children. So when we read plus 1, 2, 3, we analyze it, what we get is this hash map that has its children key that tells us, oh, I have an FN key and an RX key that you should recurse into. And then the FN that we're invoking is this var node, and it's the Clojure core plus var. So the analyzer does name resolution, right? This is something you can't tell just from the S expression. And then the RX key is this array of arguments, right? And the first argument is this const key, its value is 1. Second one is this const key, its value is 2. And it's sort of cut off, it's a little bit lower at the end, but the op of the whole expression is invoke, right? So we're going to invoke a thing. What thing are we going to invoke? It's this Clojure core plus var. What are the arguments? It's these constants, right? So this is what the sort of AST as a data structure looks like. And those are the 2 keys that are the most important. The actual analyzer itself got more complicated in the sprint to finish. And it actually has 2 subphases. It does an untyped analysis pass. So it'll just sort of manipulate. There's certain transformations that we can do to Clojure where the types don't matter. And then it has, because Magic's job is to be as performant as possible, it does a pretty aggressive type inference and type flow pass, which is a separate walk over the syntax tree. And it does that to like make sure that we hold on to as much type information as we can. Because even though Clojure is dynamically typed, there's actually a lot of type information just sort of lying around in constant values. If you ever do any interop, like we know the types of the values coming out of a static method or an instance method. So the analyzer now does a lot of work to hold on to all that type information and make sure that we can generate the fastest bytecode that we can. That bit is fairly complex, unfortunately. So we read, we analyze, and the last step is we compile. So the compile step, the compile function is taking the syntax tree that we saw in the previous slide and giving us this kind of goofy looking data structure. It's a sort of vector within a list within a vector within a vector, these hash maps. But this is what I mean. This is what I meant when I talked about symbolic bytecode. So it's Clojure data. It's a little messy, but it's an encoding of the kinds of bytecode we're going to want to give to the VM in the final step. So here we're saying, in order to run this expression, the first instruction you need is LDC I8. So that's load constant of an 8-byte integer, and the argument is 1. So this is going to load 1 to the evaluation stack. And then the next instruction is LDC I8 2. So we're going to load 2 to the evaluation stack. 3, we load 3 to the evaluation stack. Add OVF, that's add with overflow checks. So this will cause us to add 2 and 3, pushing the results back onto the evaluation stack. And then add OVF again, that'll add the result of the previous add and the 1. So the LDC I8 add OVF, those are instructions from the common intermediate language. So these are CLR bytecode instructions. And we're using Clojure data to be able to sort of manipulate them and piece them together. Because it's an object-oriented and like mutation-oriented ecosystem, there isn't really an easy way to talk about bytecodes on their own in C#. They sort of have to be part of a compilation context, and it's very much, you ask for a banana and you get a gorilla holding the banana and the rest of the jungle. So this representation makes it really easy to write a function that just returns a little bit of bytecode, and then another function that returns a little bit of bytecode, and then we could sort of concatenate them and build them up as a functional data structure. Something that's interesting here, though, is in the previous slide we said we were invoking a var, but there's no var invocation here, because the analyzer actually runs optimizations and it figures out, oh well, the plus used in this context, we don't actually have to call a function. We can use an intrinsic on the VM, so it knows about add with the overflow check. So it's able to do those optimizations. So then the last step, we have to do a little bit of a detour, just to be as complete as possible. Like I didn't want to make this sort of a magical thing because this code all actually runs in the REPL. Like I was saying earlier, to emit runnable bytecode into memory, there's a little bit of a song and dance you have to do because of how the VM works. So you actually can't just run this on the VM, right? In the CLR, bytecode can only exist within a method, and method can only exist within a type, and a type can only exist within an assembly, and within a module, and a module can only exist within an assembly. And you have to give the VM all of that really in order for it to run your code. So this is the top level API of Magic handles that, right? You sort of it puts together the bytecode and it builds the surrounding context, and it sort of runs them as needed. But this is more or less what's happening. We generate like a made up name. We add a return intrinsic to whatever bytecode we are trying to run. We put that into a method. We put that method into a type. We put that type into an assembly and a module. Emit bang writes it into memory, and we extract the type that we just made. We use reflection to create an instance of that type, and then we call the method that we sort the bytecode in. So bit of a song and dance, but in the second part, we'll talk about how this stuff becomes a source of complexity. But once you have that, that's the whole end-to-end. That's the compiler. Those are the functions that it takes to go from string to a result. Notice here that we're also declaring the type, right? Because the VM is typed. So Magic will emit conversion bytecode to turn it into an object. But when we're doing it in a low-level way, that's something we need to manage. So that's it's 4 phases that more or less map to 4 functions, right? And each of those functions takes as input a kind of data structure and produces another kind of data structure. So just to sit with the analyzer and the compiler a little bit, um, the way you get one of those, an AST map, right? So it's a hash map with op and children keywords. That starts in the tools analyzer library, and it's like nice, and it's straightforward in a way that I find quite nice. When you parse an S expression, you pull the first symbol out and you do a case to dispatch it to a parsing function. So if the first symbol is if, we're going to parse this S expression using the parse if function. And this is the entirety of the parse if function. We destructure the S expression, right? So we ignore the head because we know it's an if we've gotten here. We know the second thing is a test, and then we have the then and the end and the else. It does some error checking, but then it just gives us this hash map back, right? This is a straightforward functional transformation of an S expression into a hash map. You'll see that it'll do it's a recursive analysis, right? So the test and the then and the else are also sort of recursively analyzed, and we get this nice nested data structure. There's a mechanism in Tools Analyzer to do passes over the tree that you produce. And that's how we do optimizations and implement some other semantics. But this is the basic idea, right? We're just writing functions that return hash maps. The compiler it does a little bit more interesting things, but things that are not specific to compilers, I don't think. It's just functional programming tricks. And I want to sit with those a little bit before getting into the surprising challenges. So the job of the compiler is to take one of those AST maps, right, a hash map with an op key, and turn it into some symbolic bytecode. So it has a similar task as the analyzer, which is like, I'm receiving input and I need to dispatch which function am I going to feed this into, right? So one way to do that is with multi-methods, right? And an early version of Magic actually used multi-methods, where we'd sort of pull out the op key and we'd find, the multi-method system would find the correct body or the correct method of the multi-method, and we'd sort of feed that in. But I didn't do that for reasons that I think that ended up being like quite powerful. So instead, what we do is any AST node that is getting compiled, its op key gets looked up in a compiler map. So you see here in the AST to compiler function, the compiler function is being looked up in this compiler's parameter that gets passed in the top level compile function from get compilers. Get compilers, it does a little bit of error checking and a few other things, but it returns basically a map that looks like this. So we have a hash map of AST op keywords to compiler functions, very similar to the parse in the analyzer, right? But this is a map and not a case expression. So in the case of our if, which should be next. Right, so in the case of if, we basically look up the op keyword here and dispatch to the if compiler. And this is the entirety of the if compiler. We destructure the keys from the AST map. Now we have these tests, then else. We do a little bit of optimizations. We can figure out if an if will never hit its then or else branch, and then we basically just compile we replace the node with the respective branch. Right, so if it's always then, we just compile then. If it's always else, we just compile else. Otherwise, we recursively compile the test expression. We produce some conversion bytecode. We have some raw symbolic bytecode here. The br true is branch true. So what we're saying here is, give me run the bytecode for the test, convert it to a Boolean if you have to, and then branch to a true label if that happens to be true. If we didn't branch, then we'll end up here. So give me the bytecode for the else. We do some conversions if we have to, and we jump to the end label. BR is branch, it's an unconditional branch. This is the then label that we would have jumped to if the test was true. So we compile the then branch, a little bit of conversions if we have to, and then the end label, and then we're done. So this is like, I love looking at this because it's a mixture of basically raw bytecode interspersed with recursive calls to the compiler, interspersed with logic that's sort of making decisions about where things should go and where they shouldn't go. And it actually reads very closely to the final bytecode. Like if you look at this in a disassembler, there's a line, there's a one-to-one correspondence between most of this Clojure code and the resulting bytecode. But the interesting thing is, if compiler was passed more than just the AST that it's compiling, there's also passed the compiler map, the compiler's map, and it passes that map. It sort of threads that map all the way down the compilation. And in this case, in the case of if, it doesn't do anything interesting. It just sort of passes the map along. But having your dispatch map effectively as a first-class object becomes very powerful for the few expressions that need to intervene on it. So let is a great example of that. What let does is it gets its compiler's map and it creates a new compiler's map by creating this function that compiles AST nodes that have an op of local. So the let expression is deciding how to compile local, local bindings or like local lookups. And it's making that decision in the lexical scope where it figured out the map of, oh, this Clojure local binding is actually this bytecode binding. So the bridge between the names of your, the names get unique, but the bridge between the names of your local variables and the actual like bytecode representation of those variables gets established here in this let binding, and then it's lexically closed over in this function. And those specialized compilers, so specialized compilers now is whatever we got passed in plus our compiler for locals, that gets passed into the body and into the bindings of the let. So this way, the decision for how to turn a local variable, or I'm not a local, sorry, I've been doing JavaScript for 4 weeks, if you can tell. The decision of how to turn a local binding into bytecode is entirely decided in this function. And I've left out the construction of the binding map just to fit it on the slide, but it's another half dozen lines of code, and it all exists in exactly one place. In other compilers that I've worked on, there's this you're sort of passing around an environment or a compilation context. This is other data structures that you need in order to keep track of which local variables actually map to which, or which local bindings map to which CLR variables. But here it all just happens in the lexical scope of the let compiler, and it just gets threaded through. And so this is not a compiler trick. This is a functional programming trick, and this is saved my behind more times than I can count. The let uses it, but it also gets used in def type. It gets used in a bunch of places where bindings are a little bit funky, and we want to be able to make local decisions about them. So that's the sort of dynamic first-class dispatch that the compiler does that I find interesting and ended up being quite powerful. But that's basically it. That's those are the broad strokes of the compiler, and that was working for the most part by 2018. We had it's hard to measure the percentage of a programming language, but it's 70, 60% of Clojure compiling using just this stuff. So the takeaway for me at this stage was that if you're compiling a Lisp that's well designed and your compiler itself is functional, you're actually, I don't want to say it's not hard. This stuff is still hard to do, but it's not a dragon poking its head out of a computer monitor. It's lateral to other functional programming you may have done, right? And if you've done anything with real-time systems or user-facing systems, this is probably not even that hard. Where is what I just said? Where does it stop being the case? There's a difference between a compiler that is sort of nice and works, and something that meets the arbitrary constraints of like industry and like useful application. The sort of like TLDR of this section is when you're building a compiler, I think I certainly had a sense when I was going in that I control the universe, right? I'm directed to bytecode and I sort of decide where things go and it's like I have full control. But things actually get really complicated when you have to interface with systems that you do not control. And I found in my experience, no matter how hard I tried to keep complexity out, this is how it found its way back into the compiler. So I have a couple of examples to look at with regards to that. A great one is try in Clojure. So in Clojure, try is an expression. This is a weird way to write this expression, but it is valid, right? You could write try wherever you want, right? In the middle of an addition or at the top level of a function, it doesn't make a difference. It returns a value. According to the ECMA specification for the common language runtime, part 1, subsection 2, paragraph 4, blah, 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 blah. Entry to the protected blocks can be accomplished by fall through, at which time the evaluation stack shall be empty, which means when you generate a try in bytecode, you're marking a region as protected. You're telling the VM that like an exception might be thrown in here, or in its like the dynamic scope of this block of bytecode. Please catch the exception or like behave differently if that happens. Entering that region of bytecode, you have to guarantee that the evaluation stack is empty. So if you pushed 1, 2, or 3 to the stack and you enter that region, the VM crashes. It just like has nothing to say to you. Your bytecode is in fact not valid if you did that. So there's not a good formal reason. I mean, most VMs do this. I'm sure there are good reasons, but like this is a tension between the design of the CLR and Clojure. And it's the job of the compiler to reconcile that. So there are 2 implementations of this. The first draft wrapped all of your tries into a function and like invoked it, because within the function, the evaluation stack is empty, but that caused problems and it's quite hard to make it fast. So I copied what F# does, and the current implementation will, if there's a try in the middle of an expression, we actually recursively turn all containing expressions into let bindings that look kind of like this bottom example. So the evaluation stack is empty by the time we get to evaluating this code, and it works. It's sort of truncated for space, but this transformation is not simple. This is about 100 lines of code just to do this. And it exists because I don't control the VM, right? This is why historically, I think a lot of languages like compilers shipped with their own VMs and their own runtimes. So they could, the design of one could inform the other. But if you're sort of targeting a system you don't control, then that's that, then you don't control it. In the case of Magic, I also didn't control the source language. And I made the joke to my friends that I didn't know that when you compile the language, you have to compile the whole thing. But there are about 7 different special-ish forms in Clojure that relate to type definition, where the compiler sort of needs to know that and take special cases. So I kept finding, I really wanted like one type definition implementation, and then everything sort of leans on that. And there may be a way to do it, but there's like little differences. Like in Reify, that this is explicit, but in proxy, it's implicit. And that just means that the binding logic for implemented types has to fork on like, am I doing a proxy or am I doing something else? So that's just complexity and bloat and edge cases that come from the design of the language itself, which for the most part is very good, right? But for historical reasons, I think has a couple of these like warts, which you can ignore as a user of Clojure, but as an implementer of a compiler, you can't, right? Because the test suite won't pass. The final thing I'll end on, just to leave some time for questions, is beyond just like not controlling the VM and not controlling the source language, there's other tooling out there that you might want your compiler to interact with. So an explicit goal of Magic was to support compiling to the iPhone. And the way in Unity compiling to the iPhone works is the bytecode is taken through a pass called IL2CPP. and it literally turns your C# bytecode into C++ text. I think like hundreds of megabytes of C++ text, which it then compiles into native code because the iPhone doesn't support JIT compilation or anything dynamic. So there's this tool, this proprietary tool that we had to support. And it choked on our bytecode in really annoying and perverse ways. So here's a weird, again, all the sort of examples of compiler code are all sort of pathological by definition, but if you have a throw in the middle of a function, the next expression is unreachable. Right? You could statically know that you will never call BAS_X. Every compiler I've seen will actually delete BAS_X because you don't need it, right? I always perceived this as an optimization, and it kind of is. So Magic didn't do this for years. And it's important that I say, like, on the record, it is correct to do that. I read the spec, I ran it through verifiers. There's nothing wrong with leaving in code after a throw. The proprietary tool that we depended on to go to the iPhone choked on this kind of code because it had only ever been tested on C# code, and C# always removed code after the throw. So we had to add a pass, which again is not simple, to clean up expressions after throws just to support this tool. So it's like, despite best efforts, complexity, because of things you don't control, just kind of keep manifesting in. And that to me was the difference between a compiler that I wrote that sort of in a self-contained way, worked and was correct, and then coming out into the real world and trying to get it over the finish line and interacting with the grossness out there. I'll end with a couple of links. If you're interested in compiler stuff, I did study computer science, but my focus was in graphics, and I have no formal training in this stuff. And I think if you read parts of the Magic compiler, that might show. But I learned this stuff by watching other compilers. And there's a bunch of documentation and tools out there that make that really, really easy to do. So SharpLab, Godbolt, and AST Explorer, these are online tools where you write code in one pane and you see the sort of transformation in the other pane. And by playing with those tools, I found that I was able to begin to develop an intuition for how does this thing become that thing? And even if you're not into compilers, that's just a very fun thing to do. So I'll end with this meditation on programming language theory from Weird Twitter. And if there's time, I hope there's time, I'm happy to answer any questions.